Hello everyone, I want to welcome you to another section. In this video, I want to talk about the application of some spectroscopic techniques in the study of metal complexes. First, what are metal complexes? Metal complexes metal complexes are usually are also called coordination compounds, and majorly they are always containing a metal ion at the center, which is coordinated to surrounding molecules, which are usually called ligand. So in a metal complex, you always have a central metal atom and some molecules coordinated to this central metal atom. Example of a metal complex is given as Cu, and we have H2O6, and we have this. Now, this is an example of a metal complex ion, whereby the central metal is copper atom, and at the same time the surrounding molecule, or let me say this coordinated molecule to the central metal, is H2O, which we all know as water. So since water molecules are coordinated to this central copper atom, and that's what forms the metal complex. But this is a metal complex ion. You can also have a metal complex compound, but this is an ion. Another example also is that you can also have something like Fe, and you have H2O6. So this is another example, or yes, this is another example of a metal complex involving ion as the central metal and H2O as the surrounding molecule, which is coordinated to the central ion atom. So in a metal complex, you always have a metal which is coordinated to some molecules, which can either be neutral or even charged, and these molecules that are coordinated to the central metal are called the ligand. And majorly in metal complexes, transition metal usually serve as the central metal to which the ligand are coordinated to. So in this video, like I said, we want to look at how to use different spectroscopic techniques to analyze a metal complex. Majorly, we are going to be looking at complexes which are coordinated to organic ligands, and we are going to be looking at how we can use these different spectroscopic techniques to study this set of metal complexes, because metal complexes involving organic ligands have several applications in medicine and also in pharmaceutical. So, but the focus in this video is to give an explanation on how spectroscopic techniques are being used in the analysis of metal complexes, majorly involving organic ligands. So in this video also, I'll be talking majorly on three spectroscopic techniques, which include the UV visible spectroscopic technique, the infrared spectroscopic technique, and lastly, I'll be talking about the mass spectrometry. So these three spectroscopic techniques are the ones I'm going to be talking about in the analysis of the metal complexes. So let me start with the visible let me start with the ultraviolet visible spectroscopic techniques in the analysis of metal complexes. Metal complexes generally could absorb light in the visible and ultraviolet part of the electromagnetic spectrum, and the absorption of this particular part of the electromagnetic spectrum usually brings about um an electronic transition, from that is electron moving from one energy level to another. I'm going to be giving us the three major kind of transitions that can occur in the metal complexes due to absorption of light in the visible and the UV region. Basically, in the analysis of metal complex with visible with UV visible um spectroscopic techniques, we will always have a UV visible spectrum where absorbance is plotted against the wavelength. So the UV visible spectrum help us to know the wavelength at which the metal complex has particularly absorb light in the UV visible region. So before I go to the aspect of UV visible spectrum, first we must understand, like I said, that there are three types of transition that can occur due to absorption of light in the ultraviolet and visible region of the electromagnetic spectrum. The first kind of transition that can occur in a metal complex is what we call the intra-ligand transition. The second one that we can have is we can have D to D transition, and the third kind of transition that we can have is transition involving charge transfer. And this can either be MLCT or LMCT. I will explain what that implies. Now, let me start first with intraligand transition, because we are looking at metal complexes involving organic molecule as ligands. So it gives us a possibility of having an intraligand transition, which are some of these transitions we've talked about under the UV spectroscopy techniques. Some of the possible intraligand transitions that we can have, that is transitions that are occurring within the ligand of the metal complex, specifically the organic ligand. So the possible transition that you can have within the organic ligand includes a pi to pi antibonding transition. You can have a transition from a sigma to sigma antibonding transition. You can have a transition from a non-bonding orbital to either a sigma antibonding or even to either a pi antibonding. So all of these aforementioned transitions could occur as an intraligand transition. And one thing about intraligand transition is that they are usually seen in the ultraviolet region of the UV visible spectrum. So they always occur within the range of 200 to 400. That's where you can see the intraligand transition. And I said they include the pi to pi star, that is the pi antibonding. You can have sigma to sigma antibonding. You can also have it to be N to either pi antibonding or N to either sigma antibonding. So these are possible interligand transitions that can occur in a metal complex. And I've said two things: they occur within the ligand, the organic ligand. At the same time, the signal or the band for this particular transition is usually seen in the UV region, which is usually between 200 nanometer to 400 nanometer. For the second kind of transition, which is the major one we will be focusing about in this particular video, is the D to D transition. Basically, electron can also transit from one d orbital to another d orbital within the metal atom itself. So absorption of light within the ultraviolet visible region of the electromagnetic spectrum can also cause a D to D transition. But this transition specifically happens within the metal atom. And the reason for this transition is because as ligand approaches the central metal atom, the d orbital of the central metal undergoes a splitting such that the five degenerate orbitals split into two separate orbitals, one of some set of higher energy and some set of lower energy. The splitting pattern of the d orbital of the metal depends on whether the metal is in an octahedral environment or whether the metal is in an tetrahedral environment. That's what determines the splitting pattern. So the 5d orbital could split into something like this, could split in this form. So it could split into two set of what, of orbitals like this, and we can also have it splitting into something like this. Now this is the splitting that occurs in an octahedral environment, whereby three of the five orbitals of the five degenerate orbital we have lower energy, while two we have higher energy. But in a tetrahedral environment, two we have lower energy, while three we have higher energy. So this is what happens in an octahedral environment, and this is what happens in a tetrahedral environment. In a tetrahedral environment. But like I said, the splitting of this d orbital in a metal allows for the transition of electron from d orbital of lower energy to a d orbital of higher energy, and that's the reason behind a d to d transition. And another thing also to note is that d to d transition usually occurs in the fissile region, and it is even this transition that determines the color of the metal complex. Because when a compound absorb light in the visible region, the complementary color to the absorbed light will certainly be reflected, and that's the reason for the color of several complexes that we have. So in a way, if a metal complex absorb blue light, e probably when you check the UV visible spectrum given to you, where we have a plot of absorbance against wavelength, and you observe that the metal complex absorb light in the visible region of the electromagnetic spectrum. That implies that there is possibility of a D to D transition. But what we are trying to say is that the absorbed light will not be the absorbed light helps to determine the color of the complex, because the color reflects from the complex, or let me say the color of the complex will eventually be the complementary color to the absorbed light. So in a way, if I know the absorbed light, if I know the light absorbed by a metal complex, I can easily predict the color of the given complex, since I know the absorbed light. And that's the essence of this particular transition that occurs in metal complexes. So two things that you have to take note is that D to D transition can also occur due to the fact that the degenerate d orbitals of the metal complex undergo splitting as the metal and the ligand interact, and this splitting allows that some of the d orbitals will have lower energy, while some will have higher energy, therefore giving room for transition from one d orbital to another d orbitals. So, and I said that specifically for d to d transition, they occur within the visible region. So the D to D transition usually occurs within the visible region, unlike the intraligand transitions whose band usually occur in the UV region. Basically, the visible region of the electromagnetic spectrum starts from around 400 to around 7 or even 800 nanometers. So when you see a signal at within this particular range, you can predict that the band is due to a D to D transition. Depending on the kind of metal that you have will determine the number of bands you will have in the visible region of the UV visible spectrum. For complexes in an octahedral environment, the number of bands that will be observed for D to D transitions differs from metals to metal. There are some metals that they will give three absorption bands, that you will see three absorption bands for them in the visible region of the electromagnetic spectrum, while there are some metals that will only give a single broad band within the visible region of the electromagnetic spectrum. So basically, we have that D1 metal, D4, D6, and D9 metal usually gives just one absorption band within the visible region of your UV visible spectrum. So an example of D1 transition metal is titanium 3 plus. Example of D9 metal is copper 2 plus. So such metals as copper 2 plus and titanium 3 plus in an octahedral environment will produce only one broadband in their UV visible spectrum. While metals with D2, D3, D7 and D8 we produce three bands in the visible region of the electromagnetic spectrum as much as they are in an octahedral environment. There is an explanation to each of these particular thing that we have explained. For example, if you are considering a copper 2 plus in an octahedral environment, you know, the d orbital has 9 electrons for copper 2 plus. Therefore that implies that we are going to have an arrangement as this, because the copper 2 plus is in an octahedral environment, so we are going to have an arrangement like this. So in this case now, there is only one possible transitions that can occur in this particular case. Now compare that to probably when you also have something like chromium 3 plus, chromium 3 plus. For chromium 3 plus, so we have this particular arrangement for chromium 3 plus, and that give us a possibility of having like up to 3 transitions in the case of chromium 3 plus, which is a D3 ion. And that's why chromium 3 plus would give about 3 different signals within the visible region of the electromagnetic spectrum, especially when it is in an octahedral environment. So but just let us take note that D1, D4, D6 and D9 ions, they will always have a single broadband in the visible region of the UV visible spectrum, while D2, D3 and D7 with D8 will give at most 3 bands in the visible region of the UV visible spectrum. I've talked about what UV visible spectrum is like. That's a graph that shows absorbance, where absorbance is plotted against the wavelength. So the absorption band can always be checked to know at which wavelength absorption has occurred, and that's what we have in that particular case, and that's for D to D transition. I want to show you an example of how UV visible spectrum of this set of D ion metal and then of this set of D ion metal should look like. So for this first set of D ions, we can have the UV visible spectrum to be something like this. Let's say this is around, let's say this 200, and let's say this 400. So and let's say this is probably our 700. So you can see that here you are having just a single band, a single absorption band within the visible region, and that is what you can have in a UV visible spectrum of this first set of D elements. But for this second set of D elements, you will see something like this. You can see something like this. So you can see that, so in this case now, you can see that we have like 3 bands, which is 1, 2, and so there will be 3 different absorption bands for this second set of D elements, and that's what to expect, that's what to look out for. But don't forget what I also said, that this applies when you have this metal when you have them in an octahedral environment. That's where you can see what I'm talking about with regards to this set of D metals and this second set of D metals. And lastly, talking about the last type of transition that you can have in a metal complex that has to do with the UV visible region of the electromagnetic spectrum. That is the transition involving charge transfer. Now, for transition involving charge transfer, that involve transitions from a from either the metal, that involve transition of electron from either the metal, the ligand, or from the ligand to the metal. And that's why I told us earlier that for transition involving charge transfer, you can have MLCT, you can have LMCT. So MLCT implies metal to ligand charge transfer, while this implies ligand to metal charge transfer. So electron transition can occur from the metal to the ligand, at the same time from the ligand to the metal. Basically, transition involving charge transfer has to do with the oxidizing ability of the metal and the coordinated ligand. So if the capacity of oxidizing of the metal and the ligand is so much different, there is always a possibility of electron transiting from the metal orbital to the ligand orbital, and that's what leads to a transition involving charge transfer. Like I said, it can either be from the metal to the ligand, and it can also be from the ligand to the metal. An example of this particular absorption is seen in potassium permanganate, which is MnO4. Normally Mn2 plus, which is the metal in this particular compound, Mn2 plus is a what? Is a D5 ion. Mn2 plus is a D5 ion. So by in an environment as this, what happens when you have it in an octahedral environment as this? Now, although depending on the kind of ligand that you also have will determine what will particularly happen. For example, we have what we call weak field ligands, and we also have the strong field ligand, which determines how much energy difference occur between these two sets of orbitals. If you have a strong field ligand, that implies that the gap between these ones at the lower energy and the ones at the higher energy will be very much. And when you have a weak field ligand, that implies that the gap between this and this set of orbitals will be very small. So, but that has a way of affecting how electrons are arranged in these particular orbitals, ligands, and that implies that I'm going to have this particular arrangement. So I'm going to have this, I'm going to have this, I'm going to have this. So this is what happens when you have a low field ligand. But if it is a strong field ligand, this arrangement might not be possible. There may be what we call a force pairing. That is, electron is first of all pair up at this lower level before pairing occurring at the higher level. But when you're having a weak field ligand, whereby the gap between this set of orbitals and this one below is not that much, that is, the energy difference between this up and this down is not that much, then you will not have a force pairing of electrons, and you are going to have an arrangement as this. So in this particular case now, this orbitals is half filled, and that makes it a bit stable. So in this particular case, we don't expect a D to D transition, because the M2 plus D orbital is a stable orbital. So this will not really give us a signal for D to D transition. Yet this particular compound is colored. So the question is, what is the reason for the coloration of this? So the explanation to this is the transition involving charge transfer and not due to D transition. So on the basis of this, you can also take note that a transition involving charge the absorption band for a transition involving charge transfer can also fall a bit into the feasible region. But basically, the absorption band for a transition involving charge transfer is always found in between the UV region and the feasible region. So one can probably assume it's always between say 400, or let's say 350 to 500, and that's where you can find the absorption band for a transition involving charge transfer. So on the summary of this first aspect, talking about UV um the UV visible spectroscopic techniques in the analysis of metal complex. We've talked about the fact that metal complexes can absorb light in this particular region of the electromagnetic spectrum. At the same time, we've talked about different kind of transitions that can occur due to the absorption of light in this particular region, which involve the intraligand transition, the D to D transition, and the last one, which is transition involving charge transfer. I said that the intraligand transition are usually occurring, they involve the ligand, they involve transitions that occurs within the ligand, which I've said in this case they are what? They are organic molecules. And the absorption band for this particular transition is found in the UV region, which is between 200 to 400. And I said for the D to D transition, it occurs within the metal, and the absorption band for D to D transition is found in the feasible region between 400 to 800. And I also said that for metals that are in an octahedral environment, they can either give one absorption band in the feasible region, and they can either give and some can either give three absorption band in the feasible region. I gave us an example, and I also said that D1 metal, D I also said that D1 metal, D1, D4, D6 and D9 metals usually give one absorption band in the feasible region. An example of that is, like I said, is copper 2 plus and titanium 3 plus. Titanium 3 plus is a D1, while copper 2 plus is a D9 metal. And I also said and I also said that D2, D3, D6, sorry, D2, D3, D7, D8 metals we always produce at most three absorption band in the feasible region, provided that they are found in an octahedral environment. And I said example of D3 is chromium 3 plus, an example of D8 I think that's nickel 2 plus. So now those set of metals we always give at most we always give around three absorption band in the feasible region for D to D transitions. And the last kind of transition I talked about is the charge transfer, which involves um which involves stable which involve metals with stable d configurations, that is probably metals with d orbitals that are half filled or even fully filled. That these metals, when they are involved in when they are the central metal in the metal complex, they can also have a transition involving charge transfer, that is transmission of electron from either the metal to the ligand, or either the ligand to the metal. And I said that the absorption band for a transition involving charge transfer is usually in between the feasible region and the ultraviolet region. And I think with this we should be able to um work on any I think we should with this we have understand how to use UV visible spectroscopy technique in analysis of metal complex. So when you are given a um when you are given a UV visible spectrum of a particular complex, the first thing to look out for is the possible transition that could have occurred based on the spectrum given to you. So you look, I've said a spectrum is a plot of absorbance against wavelength. So you look at the spectrum and you look at where absorption take place within the complex. So if you know the wavelength where absorption takes place, so you can now determine, you can also look out for the maximum absorption. That is, because you can imagine when you have several wavelengths where absorption takes place, you will now have to also consider where you have maximum absorption out of all the absorptions that take place. So you can use that to determine the color of the complex. So for example, let's say in a metal they gave us the UV visible spectrum of a complex to be like this, and let's say they said this point is 500 nanometer. Now I've said this wavelength, is absorbance. So now for this, the first thing that comes to my mind in this case is that the metal complex gives only one broadband in the world. Let's say this is 200, this is, let's say, 400, and let's say this is 500, and let's say this is 700 nanometer. So the first thing that should come to my mind is that this particular metal complex give only one broad absorption band in the visible region, and that would probably implies that the metal involved in this complex is either a D1, a D4, a D a D a D6, or even a D9 aeon. So, and that's the first. Another thing is that I can also, like I said, determine the color of the complex. Since I know, in this case, for example, in this case now, the absorption band, the absorption takes place at what? At 500 nanometer. So I can use that to determine, okay, what's the color absorbed. So what's the color? So you have to determine the color of light that has a wavelength of 500 nanometer. So when you know the color of light that is absorbed by this particular complex, so the complementary color to the color absorbed will be the color of the particular complex that is given unto you. And even in some cases, they can also ask you to convert the wavelengths of light absorbed by the metal complex, to convert it to wave number. And so don't let us forget that we have that wave number will be equals to 1 over the wavelength, which is, and it's usually given in what? In per centimeter. So they can ask us to do that conversion. They can ask us to determine the color of light absorbed by the complex. They can even ask us to determine the color of the complex itself. And I've said the complementary color to the color of light absorbed by the complex will be the color of the complex. So if your complex from this particular spectrum absorb light at 500, so you have to determine the color of light at 500 nanometer. At the same time, find the complementary. So let's say now, if the color of light absorbed at this, if the color of light for this 500 nanometer is, let's say, red, so that means that the color of light absorbed by the complex is the red color of light. So the complementary color to red will be the color of the given complex. And those are some of the things that they can ask us in the exam.